All right, we're moving on to Gauss's law. This time we're going for a long, charged, non-conducting cylinder. So this is going to actually be one of the more complicated ones to look at. So let's say this is the front view of my cylinder. We're going to be placing inside of this cylinder our Gaussian surface radius r when r is less than a. And what we're after here is finding out how much charge I'm enclosing here. And again, we're going back to this idea of rho, which is charge per unit volume. But again, since this is infinitely long, we're not really actually concerned with an actual charge per unit volume. So we're going to be given a rho. What we need to do with that to find our enclosed charge, Q enclosed, is as always rho times the enclosed volume. In this case, my enclosed volume is the volume I have enclosed by my new Gaussian surface. Well, in this case, it's going to be this area here, area, times the length of my cylinder. It says pow, you get that. It's going to be rho times pi r squared times the length of my cylinder. This is what we're going to use for Q enclosed inside of a uniformly charged wire or cylinder. So, with this cylindrical symmetry, we're doing two things. One of them is looking at the electric field outside. So we'll do that here real quick. A distance of r away. So in the case where r is greater than a, okay, given rho for this entire thing, we're going to have E dot dA is equal to Q enclosed over epsilon naught. Given a rho, it's E times 2 pi r L, the surface area of this thing, which never changes, is equal to rho times the volume enclosed, okay, which is the area of the thing, pi a squared times the length inside of here. This part inside of here is the only charged volume that I'll be enclosing. That's all we're concerned about over epsilon naught. So again, this goes away, and in this case my pi's will go away. And the electric field is equal to rho a squared over 2 epsilon naught times r. And this looks a little bit different than what we had before, but what's notable is that it's decreasing as 1 over r, which is what we had before. Now the new part of this is when we're going to put our little cylinder inside of our charge distribution. And again, that's looking at this thing right here. So in the case where r is less than a, E dot dA is equal to Q enclosed over epsilon naught. And again, that's E times 2 pi RL. This side of Gauss's law for us is never going to change as long as we're talking about a cylinder or a wire. And that's equal to my enclosed charge. Okay. This time it's not pi a squared. We're only enclosing r squared. So rho times pi r squared L over epsilon naught. R goes away and L goes away. One of my R's, one of my L's. This pi and this pi. And the electric field here is equal to rho r over 2 epsilon naught. We see here that this is increasing like r. So looking at the electric field as a function of radius, electric field radius A, we increase linearly until we get to the outer surface, and then we decrease like 1 over r, just slightly less steep than 1 over r squared. That's what this is saying.